Okay, so let's solve some more problems. So problem 1. What are the conjugacy classes in D4? Recall that D4 is the dihedral group with 8 elements. It's the group of automorphisms of the square graph with 4 vertices. I'm drawing the square graph here. Which has 4 vertices, 1, 2, 3, 4. And D4 has, we've seen, 4 rotations including the identity and 4 reflections about various axes. Many ways to solve this problem. I'd suggest that you pause your video and try to work it out yourself and then come and see how I solve it. Okay, so to understand the conjugacy class in D4, let's firstly understand that these are all really permutations. So D4 is a subgroup of S4, and the way we've described this group, all the elements of D4 are permutations. And now suppose we have that Gx G inverse is equal to x prime for G and x in D4. So that means that x is conjugate to x prime in D4. But then that also means that G is in S4 just because D4 is in S4. So that means that x and x prime, which happen to be in D4, are also conjugate in S4. So x and x prime are conjugate in S4, which means that they have the same cycle type. Okay, we've seen that two elements are conjugate in S4 if and only if they have the same cycle type. Now the other way, the converse may not be true, that if two elements are conjugate in S4 then they are conjugate in D4, because just because you can find G in S4 such that Gx G inverse is equal to x prime, it doesn't mean that you can find G in D4 such that Gx G inverse is x prime. But this is enough to get us some crude idea of what the conjugacy classes would be like. So let's just try to write down the cycle types of the 8 elements in D4, and it turns out that those cycle types can be easily read off by the geometry of what's happening in the dihedral group when we express it as the automorphisms of the square graph. So let me make a table here where I will write down the different types of elements and I'll write down their cycle types. So the first kind of element that we have is obviously the identity element. Okay, and what is its cycle type? Its cycle type is 1, 1, 1, 1. It has 4 1 cycles. Okay, and then what do we have? We have rotation by plus or minus 90 degrees. So one of these takes 1 to 2, 2 to 3, 3 to 4, 4 to 1, and the other takes 1 to 4, 4 to 3, 3 to 2, and 2 to 1. Both these have cycle type 4. Okay, and then we have rotation by 180 degrees, plus or minus, doesn't matter. So that takes 1 to 3 and 2 to 4. So this has cycle type 2, 2. And then we have two kinds of reflections. We have reflections about axes that pass through edges. Okay, so we have reflections, I'll call these about green axes. So let's take the reflection about the vertical axis for example. So that takes 1 to 2 and 2 back to 1, 3 to 4 and 4 back to 3. So its cycle type is also 2, 2. And then we have reflection about the vertical axis, which takes 1 to 4 and 4 to 1, 2 to 3, the horizontal axis, and 3 to 2. So that's also 2, 2. So there are 2 elements of this kind. So let's also keep track of the number of elements of this kind. So here there's one identity element, there's 2 rotations, one by plus 90 degrees, one by minus 90 degrees, there's one here. These reflections, there are 2, so we've got 3, 6. We have to find 2 more elements, and these are going to be actually reflections about these diagonal axes which pass through the vertices. Reflections about purple axis. And what is the cycle type here? Let's look at this axis that passes through 1 and 3. That reflection fixes 1 and it fixes 3, and it changes 2 and 4. So it's 2, 1, 1 is the cycle type, and there are 2 such elements. Okay, so certainly elements with different cycle types cannot be in different conjugacy classes. And now all we have to find out is whether elements of the same cycle type are in the same conjugacy class or not. So of course this is a conjugacy class by itself. Now rotation by 180 degrees is of cycle type 2, 2. So we don't know, it could be in the same conjugacy class as reflections about green axes or not. Okay, and rotation by plus or minus 90 degrees, well, they are the only 4 cycles. So either these 2 elements are in the same conjugacy class or they are in different conjugacy classes. But let's look at this rotation. 1 goes to 2, I'll write down the cycle rotation. 2 goes to 3, 3 goes to 4, and then we have another rotation which is 1 goes to 4, 4 goes to 3. Well, maybe I'll write it in the same order. Two, 3, whoops, 1, 4, 3, 2. So to conjugate this, which I'll call R, and this, which I'll call R inverse, we need to find a permutation which takes somehow the vertices of this cycle to the vertices of this cycle. So we take W to be 1 goes to 1, 2 goes to 4, 3 goes to 3, and 4 goes to 2. Then we'll have so 2 goes to 4, so that's W, and so if we take R inverse W, let's take W, R, W inverse, then W inverse takes, so what this W does is it basically interchanges 2 and 4. So so W, R, W inverse of 2 will be, this will be R inverse, as we have seen in our discussion of conjugacy classes in SN. So these 2 elements also form a single conjugacy class. Okay, let's see what we can do about reflections about green axes. We'll come to rotation by 180 degrees later. So what can we do about reflections about green axes? So right, so there are 2 of them, and I'll write down their cycle decomposition. So there's 1, 2, 2, 1, 3, 4, 4, 3. This I'll call it maybe X, and the other one is 1, 3 sorry 1 4 and 2 3. Let's call this x prime. And now we can write w by just taking 1 to 1, 2 to 4, 3 to 2, and 4 to 3. Okay, but what is that element? No, that element is not in the dihedral group. So let's try a little trick here. Let's write this cycle in the other way down, round 3 2. Yeah, so now we'll have 1 goes to 1, 2 goes to 4, 3 goes to 3, and 4 goes to 2. And then indeed we have w is just it fixes 1 and 3, and it interchanges 2 and 4, so it's a reflection about one of the purple axes, and we'll have wx w inverse equals x prime. So indeed these two elements are in the same conjugacy class. And then let's look at reflection about purple axes. So then we have two fixed points. So the first element about the axis 1 3, it will have two fixed points, 1 and 3, and it will have 1 2 cycle, namely 2 goes to 4. And the other one is has fixed points 2 and 4, and it has a, so let's call this x, and x prime interchanges 1 and 3. So we can write w as 1 goes to 2, 2 goes to 1, 3 goes to 4, and 4 goes to 3. Now this element is a reflection about a green axis, reflection about the vertical axis, and we have w x w inverse is equal to x prime. So these definitely form a conjugacy class. So the elements, the identity element is in a conjugacy class by itself. The two rotations by 90 degrees are in a conjugacy class by themselves. And these reflections about purple axes are in a conjugacy class by themselves. And the only thing we don't know is whether rotation by 180 degrees is in the same conjugacy class as a reflection about the green axis. So let's see what we can do about that. So let's draw the cycle type here for rotation by 180 degrees. So we'll call that r squared, and it has cycle type 1 goes to 3, and 3 goes to 1, and it has 2 goes to 4, and 4 goes to 2. And the other element, let's take one of the reflections about green axis. Let's say 1 goes to 2, and 2 goes to 1, 3 goes to 4, and 4 goes to 3. Okay, we'll call this element x, and we want to know whether r squared is conjugate to x or not. So now if you have permutation w which conjugates them, then it must take the cycles of r squared to the cycles of x. So if it takes 1, if w of 1 is equal to 1, then we must have that w of 3 is equal to 2. And but then you see W of 1, 1 is adjacent to, is not adjacent to 3, but 1 is adjacent to 2. So no element of D4 can do this. So this is not possible in D4. Okay, but maybe W takes 1 to 2. If it takes 1 to 2, but it must still take 3 to 1. And 1 and 3 are not adjacent to each other, but so if W1 is equal to 2, then W3 must be equal to 1. Okay, but 1 and 3 are not adjacent to each other, but 2 and 1 are adjacent to each other. So again, W cannot lie in D4. And similarly, you can check that if W takes 1 to 3 or W takes 1 to 4, there is no element W and W r squared W inverse is equal to X, then W cannot lie in D4. So what we have is that this is a conjugacy class all by itself, and this is a conjugacy class all by itself. So let me just summarize this. So the conjugacy classes in D4, there are 1, 2, 3, 4, 5 of them. So they are basically identity, rotation by plus or minus 90 degrees. So this class has size 1, this class has size 2. There's rotation by 180 degrees, this class has size 1. There's a reflection about an axis through an edge. So these are the green axes. There are 2 of these, and there's reflection about an axis through vertices, and there are 2 of these as well. Now this may not have been the fastest way to do this computation, but I like to do it like this because it was kind of conceptual. It actually tells you what the different types of elements in D4 are and why they are in different conjugacy classes. Problem 2. What are the subgroups of D4? Now there are many ways to do this problem as well, so I'll let you pause your video and try it, see how many subgroups you can find, and then come back and see if you found them all. Okay, so here's the solution. Now firstly note that the order of a subgroup of a group divides the order of the group. This is because the group is a disjoint union of cosets of the subgroup, and each coset of the subgroup has the same size as the subgroup itself. So now D4 is a group of order 8, which means that its subgroups can be of order 2, order 4, or order 8, and of course there's a trivial subgroup of order 1. So basically we need to figure out what are the subgroups of order 2 and the subgroups of order 4. Now a subgroup of order 2 would just consist of the identity and one more element, and that element better be an element of order 2. That means it's an element x such that x into x is the identity. Now we've already played with the dihedral group of order 8 enough to know what these elements of order 2 are. Let me just remind you. So this dihedral group of order 8, we have let's just have another one here. Okay, so we have now reflections about vertical and horizontal axes. So we have reflection about this axis and this axis. We also have reflections about diagonal axis. So if we use the notation from earlier, oops, this didn't come out so well. Let me try again. Yeah, I've used the notation from earlier where we had S is equal to 1, 4, 3, 2, and R is equal to 2, 3, 4, 1. So this S is reflection about one of these orange axes passing through 1 and 3. So it just interchanges 2 and 4. And R is rotation by 90 degrees. Then in terms of these elements, S and SR squared are the reflections about these axes. So the reflection about this axis is S, and the reflection of this axis is SR squared. And these two are the reflections RS and SR. Okay, so there are 4 of these reflections in the dihedral group, and there's another element of order 2. R squared also has order 2. So the subgroups of order 2 in the dihedral group So it's a subgroup consisting of one of these 5 elements and the identity. I'll use the notation angular bracket. So what this means is that this is the smallest subgroup that contains the element R squared. So this angular brackets R2 is the subgroup which contains the identity element and R squared. Similarly, we have the subgroup RS, we have the subgroup generated by SR, we have the subgroup generated by S, and we have the subgroup generated by SR squared. These are the 5 subgroups of order 2. What about subgroups of order 4? So the subgroups of order 4, well, we know that a group of order 4 is either cyclic of order 4, that means it's just generated by one element of order 4, or it's Z mod 2 cross Z mod 2. And so it's going to be generated by 2 elements of order 2 which commute with each other. And so the only element of order 4 in D4 is the element R. So the subgroup of order 4 is R, that's isomorphic to Z mod 4Z. And then there are, if you look at these elements RS and SR, well, they commute. RS into SR is R squared, as is SR into RS. So they generate a subgroup of order 4. And then S and SR squared, they commute. S into SR squared is R squared, which is also S R squared into S. So the smallest subgroup containing these things. So just to be clear, this subgroup R consists of 4 elements: E, R, R squared, R cubed. The subgroup RS, SR consists of 4 elements: identity, RS, SR, and R squared. And finally the subgroup SR squared consists of 4 elements: identity, S, SR squared, and R squared. Okay, and then there's the obvious subgroup of order 1, which is just singleton identity, and the subgroup of order 8, which is all of D4. We can organize these subgroups in a somewhat appealing manner, showing how they are related to each other. So at the bottom of this pile, we have the trivial subgroup consisting only of the identity element. And then we have, we have the subgroup generated by R squared, and then we have, the subgroup generated by S, the subgroup generated by R squared S, the subgroup generated by RS, and the subgroup generated by SR. Those are the 4 reflections. Okay, and they all contain the trivial group. Now come the subgroups of order 4. So there's the subgroup R generated by R of order 4. So it consists of identity R, R squared, R cubed. That contains the subgroup generated by R squared. Then there's the subgroup R squared S generated by R squared S and S. So it contains R squared S, it contains S, but it also contains R squared. And then there's a subgroup generated by SR and RS, and that also contains R squared, it contains SR and RS. And then we have D4, the whole group. So this picture gives you a bird's eye view of all the subgroups of D4. Problem 3. Which subgroups of D4 are normal? Okay, so we've just worked out what all the subgroups are, and I'll let you pause your video and try to figure out which of those subgroups are normal and which ones are not. Okay, so to see which are normal and which are not, we need to combine our understanding of conjugacy classes and subgroups. So remember, what are the conjugacy classes in D4? So the conjugacy classes are, there's the class of the identity, there's the class of R squared, there's the class of R and R inverse, and then there's the class of RS and SR, and then finally there's the class of S and R squared S. So these are 1, 2, 3, 4, 5 conjugacy classes, and a subgroup is normal if and only if it is a union of conjugacy classes. So obviously the trivial group is normal, right? So let's just put a green highlight on the normal group. So this one is normal. R squared is conjugate to itself, and this group consists only of the identity in R squared, so it's a union of two conjugacy classes. So this one is normal. D4 is obviously normal. The subgroup generated by R consists of identity R, R squared, R cubed, which is R inverse. So this one is also normal. It's a union of conjugacy classes. Now what about this R squared S? Well, this subgroup contains R squared S, but it doesn't contain S. So this group and this group are conjugate to each other. They are not normal. So let's use a different color here. So these are not normal. And similarly, RS and SR are conjugate, so these subgroups are not normal. On the other hand, if you look at the subgroup R squared S comma S, it is a union of conjugacy classes. So this one is normal and this one is normal. Okay, so that's the solution. There are 4 subgroups of D4 which are not normal, and the remaining 1, 2, 3, 4, 5, 6 subgroups are normal. Problem 4. Which subgroups of the quaternion group are normal? This quaternion group was a group that we met in the solved problem session of last week. So this was a group which had the elements plus or minus E, plus or minus I, plus or minus J, plus or minus K, where I, J and K and E were certain 2 by 2 matrices. And we had worked out the conjugacy classes to be singleton E, singleton minus E, plus or minus I, plus or minus J, and plus or minus K. We had also worked out the subgroups. There were 3 subgroups of order 4. They were generated by each of the elements I, J and K. So the subgroup generated by I consists of identity, I minus E minus, no, it consists of identity, that is E, I, minus I and minus E. This consists of E, J, minus E and minus J. This consists of E, K, minus E and minus K. And all these subgroups contain the subgroup consisting of plus or minus E, so I would call it the subgroup generated by minus E. This is a subgroup of order 2, and then there's a subgroup E of order 1. So from this information you should be able to see which subgroups of Q are normal. So pause your video and try to see which subgroups of Q are normal. Okay, let's see if you got those right. So this is obviously a normal subgroup, right? It's just a single conjugacy class. This is a union of two conjugacy classes, the conjugacy class singleton E and singleton minus E. This subgroup, the subgroup generated by I, consists of, right, as I said, it consists of E, I, minus E, minus I. So this is also normal because it contains all this element is a class by itself, this element is a class by itself, and these two form another class. So it's a union of conjugacy classes. So this is also normal. Similarly this, hey, and of course this is normal. So this is an amazing fact. The quaternion group is an example of a non-abelian group, all of whose subgroups are normal. This is not a very common thing. So here's another nice special feature of the quaternion group.